Hello, we're group 2 for ME4351L, and this is our project report for our eddy tachometer. So, at a glance, eddy tachometers are a pretty ubiquitous measurement tool, and they use induced magnetic fields and springs to measure speed. One of the most common examples that's very easy to find is in the dash of your car. Um, they're found there to measure your speed, and they're connected to transmissions. But they're also used as in other areas and also as standalone instruments. Because of how simple the effect is, they're often very compact and robust. So as for that theory, it's very simple. So a rotating magnetic field will generate small eddy currents, which cause drag torques in some materials such as aluminum and copper. Um, so on the right there, you can see the basic design being put to work where we have on the left side an aluminum disc, and then on the right side, magnets are installed in the measurement side, that right side. Um, so the basic steps for producing this effect are as follows. So first, the rotation of the magnet side of the shaft causes that induced magnetic field that's rotating. And then as a result, the dial side, so the aluminum disc, will experience a small rotational torque from those eddies that are generated by the rotation. And so the dial shaft rotates just a little bit against a spring to produce a constant, steady reading. So, as for the design of this basic setup for our sensor, you can see we have 6 holes for magnets, um, and we designed it so that the magnets reverse polarity around the circumference of that circle of that dial. And so this produces a better effect generally than if we were to stack all north on one side and all south on the other. Another advantage of doing slots in our magnet side dial or cylinder is that we can actually stack magnets so that we can get a higher effect if we need to for the magnets, or if the magnets aren't strong enough, we can attach more magnets. So as for the housing components, this is pretty much all 3D print filament. So it's super easy to assemble. We took a lot of inspiration from more compact eddy current tachometer measuring devices that you can kind of just like attach to anything. Um, these housings were made in mind of that. So all you really need is a level surface and then the connections to make a measurement. There is a big space um, in the middle there with those big circles that hold the aluminum disc and the magnet disc together. Those are for 1/2 inch bearings. That's what we designed them for. Um, as well, the shafts are glued to their respective discs. And finally, you can see that there are sort of bridges at the ends of each of the housings. Those are for motor components for the magnet side and for a torsion spring and the dial, the measurement dial output on the other side.
The motor we chose to run this setup was a 12-volt DC motor, and we're powering it through Arduino. We're using a L298N motor driver and a 12-volt battery supply, as well as a potentiometer to adjust the speed. The shafts and bearings that are attached to the motor is a 1/2 inch diameter 3D printed shaft, and each side of the housing component also holds roller bearings to support the shafts.
Onto our digital output, we have a laser sensor module that is run through Arduino. on both sides of our housing components. And then we have an LCD screen that you can see on the right side of the screen that displays the RPMs. And then we also did a 3D printed sensor wheel. So the way this digital output works is there's code written that calculates the RPM of the speed when the sensor is disrupted 3 times. And then that speed is displayed on the LCD screen.
As for the mechanical output, as we outlined previously, now you can see on the picture there the whole thing put together. So, ideally, we would use a torsional spring or a spiral torsion spring to replicate the correct torque resistance to get our constant reading. But in this case, because of how small scale our project is, we ended up opting for a weaker linear spring that's attached to the housing and then the side of the shaft. So you can see in the picture, one end is attached to that bridge, and then the other is attached and glued um, to the side of the shaft, with the ends of each being bent 90 degrees to get this connection correct. Um, you can also see that loose fit dial there, which can be adjusted. So when the spring is twisted from the eddy effect, it's going to provide a weak but viable resistance to the motion. And so we can concentrically position the pointer and the dial with the shaft to very easily get the reading that we want.
So here we have our implementation setup. So basically we divided up the mechanical components, as you can see on the left. So that is the dial and spring and pointer that was just discussed. Then in the middle, we have our digital components. So that is the laser sensor, which is actually seen on both sides of those housing, and then the dial. And then on the right is our full prototype seen together. So you can see there is our LCD screen that is programmed through Arduino. We have an Arduino on both sides of our housing. So one is controlling the speed of the motor, and then the other one is controlling the laser pointer and the LCD screen.
For calibration of our setups, for our physical system, we have a dial that is marked radially with a 1/5 inch spacing between the markings. And the calibration was performed using a least squares curve fit and data points at each 1/4 of a dial space. And the dial pointer is a close running fit to the torque shaft, allowing for easy adjustments. The dial markings can also be labeled by whoever is using the device. For the digital system, we used a motor speed of 100 RPM, and the Arduino laser module system is used to record the actual speed of the rotating shaft using the four spacings that we have. And the laser module detects linear passes of the 4 tabs attached to the rotating shaft and converts it to RPM, which is then showed onto the LCD display.
So for testing and evaluation, we initially started with a smaller motor. And then when we implemented it, it did not induce an eddy current onto our system. So we decided to use a drill to test out if a higher motor speed would induce the current, which we found was effective when we tested it that way. So we purchased a larger motor to produce that current. And unfortunately, during our final testing, that larger motor still was not inducing the sufficient RPM needed to make the eddy current effect.
In conclusion, through this experiment, we learned that the eddy effect does not happen if the motor speed is not fast enough. So therefore, in the future, we have to test using a faster motor to ensure better results, or we tell whoever is using our system to use a fast enough motor. Our future goal is of creating a smaller tachometer to emulate real life examples, resulted in capability issues that could be improved in further iterations of our design. Thank you.
Here are some references and then our bill of materials.